All right, pre-calculus, welcome back to 4.1, part 2, getting into polynomials. So for the remainder of this, we're going to look at some multiplicities and get into some other fun stuff about polynomials. We've already kind of mentioned the end behaviors and some just some properties that we see when we're looking at even and odd functions. So here we go, guys, for multiplicities. Here's the deal with multiplicities. After something has been factored, okay, so that's important. After you have factored something and broken it down into its most simplest form, simplest parts. For instance, this guy here, this is a factored form of a polynomial. Okay, when we have it down to its factors, what we can do is we can look at the various factors and the exponents that are on them. Okay, so in this case, we have 3 factors. These 3 things are called factors. We can multiply them all together and find our original polynomial, but these are the simplified form, right? Simplified, most broken down form of the polynomial, which is in factored form. So multiplicities are just looking at the exponents on the factors. Okay, and they're going to tell us something interesting about the graph. So notice here, this first part, this first factor here is to the 3rd power. When it's to the 3rd power, again, this is already in factored form, that's very important. The multiplicity of this factor is 3. Okay, because it says here because the exponent on the factor x is equals 0, x minus 0, or of x minus 0 is 3. Yeah, so it just basically is raised to the 3rd power. If you go to the next one, what makes this thing go to 0 is -1, and -1 is a 0 of multiplicity 1 because the exponent on that factor is 1. Okay, for the first one, what makes this whole thing go to 0, by the way, is 0. So 0 is the multiplicity, has multiplicity 3. Okay, and then what makes this one go to 0 is 3/4. So again, we're going to have a 0 there. We're going to have a crossing, and I'm going to show you a picture of what this looks like. But at 3/4, we have a multiplicity of 2 because it's squared. Okay, so now, just to be clear, on our graph, we have zeros at the factors. So we know that this graph either crosses or touches at 0, at -1, and at 3/4. Something happens on the x-axis in those 3 spots. So here at 0, at -1, and then at positive 3/4. Okay, there's something happening at all of them. Now, let's get into what these multiplicities help us see in the picture. All right, so if you were to graph these, which I highly encourage you to do, but I'm not going to take the time to do it here on this lesson, you would see something interesting. And that interesting thing is, did they not give us, oh, they didn't even give us the definitions here, which is interesting. But what you would see is this. Since on our, so I'm kind of skipping through here, but since on the first 0, we have an odd multiplicity of 3, okay? Here's the rule. If a 0 is even multiplicity, okay, and I'll tell you why this is in just a second, but right now just think about the rule, then the graph is going to touch the x-axis when it's coming through, but it's not going to go through the x-axis. So it's going to come down, touch, and then turn around. If it's odd, it's going to go through. Okay, because the sign changes when it's odd. So the graph will actually cross at the x-axis if the multiplicity is odd. So we had 7x to the 3rd power. That is an odd multiplicity, and the 0 happens at 0, because if you plug a 0 in for x here, it makes that thing go to 0. So I know that that graph goes through at 0. Then we said what did we say again? That the second one, -1, has an odd multiplicity of 1, right? So at, I guess I'll keep it here. At -1, we also go through the graph. So the graph is coming through, and it could be going in the other direction, but at least I know that. And then at 3/4, it's even, so it bounces there at 3/4. Okay, and so, and if we multiplied all these things together, we know that we would have in either it'll be an even function. So if you multiply these x's together, you'd get an even function. So it's probably going to go off and do something like this. So it helps us to see what happens at the x-axis. Okay, let's look at example 6. So for the polynomial function, it says find the x and the y-intercepts of the graph of f. So what's cool about this is the factors, since this is in factored form, this polynomial, I can tell you that I have x-intercepts at 3 and at -4. Because if I plug a 3 in, I get a 0, right? And if this is equal to y, and one factor is 0, then the whole thing goes to 0. So I know on my graph that something on the x-axis, I have something happening at +3, because that makes that go to 0. And then I also have something happening at -4. Using what we just learned, we can see here, and you can also just graph this. So it says use a graphing utility to graph the polynomial function. I'm not going to do that right now, but you can do that, or you can use Desmos. But here I know that my 3 has a multiplicity of 2, okay, because in factored form, it's 2. If it has an even multiplicity like that, I know that it's going to come down and touch this graph, but it's not going to go through. I also know that if I multiply these things together, that my leading coefficient would be an odd. So I know that from left to right, this thing is going to be going in opposite directions, right? And then here it says that at x plus 4, we have a multiplicity of 1, so it's going to go through there. So, and then it says to find the y-intercepts, right? So if you found the y-intercept of this thing, this happens when x is 0. So the y-intercept happens when x is 0. So if we did 0 minus 3 squared times 0 plus 4, we would get -3 squared, which is 9. And then here would be 9 times 4, which is equal to 36. Okay, so if you graphed this up at +36, as long as I did my math right there, we would have a crossing of the y-intercept, the y. So what I'm thinking here is, since this is a positive, it's going to go up from left to right, and we know that it's going to go through here at -4, but it's going to bounce here at 3. So I can kind of understand the picture without pulling out my grapher, because I can find that intercept, and I know now that this bounces here, and then it kind of goes off like this. And let's just take a look at what they got for a picture, and there you have it. So you can see that it came through there at -4, and it bounces at 3, and that deals with multiplicity, all right, the multiplicity of the factors. All right, so that's helpful, knowing these rules. So make sure you get these rules in your notes, that if you have a 0 of multiplicity that is even, it touches, and if it is an odd 0 multiplicity, it crosses. That's going to help us kind of sketch some graphs. Then we're going to get into some turning points. Where does a graph turn and change direction? So if f is a polynomial function of degree n, then f has at most n minus 1 turning points. What that means is if the leading coefficient is 5, then at most we're going to have 5 minus 1 turning points. We're going to have 4 turning points. Okay, so if we have a degree 5 function, we have at most 4 turning points. If the graph of a polynomial function f has n minus 1 turning points, then the degree of f is at least n. So that's just saying the reverse is true. So if I see on my graph something like this, I have a turning point here, I have one here, I have one here, I have one here. It's wherever it changes direction. So this guy has at least 4 degrees. Okay, so, sorry, at least 5 degrees. This is at least a 5 degree, but it could be more. So 5 degree or more. Okay, because this is talking about at most. Doesn't necessarily mean that we have a turning point for every degree of n minus 1 degrees. So example 7 says identify the graph of a polynomial function. Which of the graphs in the figure could be the graph of a polynomial function? For those that could, list the real zeros and state the least degree that the polynomial function can have. For those that could not, say why not. Okay, so for this one, the first one here, we know that this is not a polynomial because we have a sharp turn. Okay, so that is not a polynomial. For C, we have to lift our pencil here to finish that graph, so this one is not as well. So the only one that works is B. Okay, so we would say that B is the function, that is a polynomial, and then it says to list the zeros. All right, so let's list the zeros here. We know that we have a 0 at -2, even though you can't see the negative sign, at 0, so -2, 0, and 2. All right, we know also that since this thing turns 2 times, that the highest degree here of this polynomial is 3. Sorry, not the highest, the least degree is 3. So it's at least degree 3. So it's degree 3 or more because it has 2 turning points. And since I have 3 zeros, I know that it's going to be a degree 3, right? Because if I were to, if these were just to 1 power each, this would be like x plus 2 times x minus 2, right? These would be the factors if those are my zeros. Those would be the factors. If I multiplied those out, I'd be in a degree 3, right? But since these go through here, I just know that those are odds. So each one of these has multiplicity of 1, but I could have said, well, maybe x plus 2 has a multiplicity of 3 or something like that, right? We don't know. So we just know that this is at least a degree 3. Okay, so then they walk us through that here. In behavior, we just know that, and I think I've already mentioned this, that whatever is out in front, okay, if you put this thing in standard form, you put a polynomial in standard form, the power function in front will tell us what the graph looks like. So if the first term is something like x to the 3rd power, okay, if I have something like this, then I know it's going to act like the x to the 3rd function, right? So something that looks like this. It's going to act something like this. Okay, so example 8 says identify the graph of the polynomial function. Which of the graphs could be the graph of x to the 4th plus ax to the 3rd plus bx squared minus 5x minus 6, where a is greater than 0, okay, so this is like 2, and b is greater than 0, maybe it's 3, just plugging in some possibilities. So basically they don't give us those because they don't want us to try to figure this out and plug it in. But you could plug in something like what I just plugged in and see how that works. But really they want you to see, okay, this thing is going to act like x to the 4th. That is an even function, so it's going to go off in the same direction, and it's positive. So right away, right now, what I can cross off is this guy, because this would be a negative even function, right, because it's facing downward. So that one does not work, all right? This is a degree 4, so now I'm thinking through some other things here. At most, this thing can have 3 turning points, right? Because we could take the 4, subtract 1, and that's the most turning points it can have. So let's count some turning points. This one has 1, 2, 3 turning points. So this has 3 turning points. This one has 1, 2, 3 turning points as well. And then this one has 1, 2, 3, 4, 5 turning points. So just by looking at turning points, I can now eliminate this possibility. All right. And now we're down to these 2 graphs. Now, the next thing that I would want you to think about is, what's my y-intercept, right? These have different y-intercepts, these pictures. So if you plug a 0 in for all of your x's, then what happens is this goes away, this goes away, this goes away, this goes away. If I plug a 0 in, I'm at -6. So which one of these crosses at -6? Answer B. Okay, so that is going to be my answer, and that is how I found it without fully graphing it. And let's just see